Alrighty, so I'm going to discuss reduced row echelon forms of a matrix. So to discuss reduced row echelon, we must first talk about regular row echelon, sometimes called just echelon form of a matrix. This is really important in row reduction methods for linear systems, um, norm namely Gauss-Jordan elimination along with Gaussian elimination. So to start off, let's discuss about row echelon. So a matrix is in row echelon form. I'm just going to abbreviate it from now on to be ref, since we're row echelon form. So it's in this form if it satisfies three properties. So first of all rows of zeros are beneath non-zero rows. This is pretty straightforward. Just to show you a quick example. If we have a matrix like 0, 0, 1, 2, this is not allowed because this column must be at the bottom. To fix this, it would have to look something like this. Yeah, this would be right. Alrighty, so the second property is that, each leading entry, sometimes people call these pivot points. So each leading entry is in a column to the right of the leading entry of the row above it. This may seem a little wordy, but it's really quite simple. So if we have a matrix like 1, 0, 0, 1, 1, 0, 0, 1, 1. Oh wait, excuse me. That was the wrong example. If we have a matrix like this is clearly not an echelon form since it violates this property. Namely, the leading entry of the third row, this one right here, is not to the right of the leading entry of this row. This violates this property. Must look something like this, for example. This is perfectly good. And the last property is that all entries below a leading entry or pivot point is 0. Oh, I don't know what happened there. Is 0. Yep. So if we have a matrix like this violates this property since the leading entry right here has a 2 beneath it, which is not allowed. So this is wrong. So if any matrix has these three properties, it is in row echelon form. Alrighty, now that I've discussed row echelon form, I'm now going to take it up a notch and finally discuss reduced row echelon form. So reduced row echelon form also holds the same property as regular row echelon forms. It has the three properties that I've already discussed plus two more, and I'm about to discuss them. So to start off, let me just write it down. A matrix is in reduced row echelon form if it also satisfies these properties. All right, so to start off, each leading entry must be 1. I mean, it's pretty straightforward. So each leading entry is 1. So like I said, straightforward. You have a matrix like this. This is good to go. But a matrix like this, 3, 1, 1, is not allowed since, the leading entry is 3, not 1. And the second and the last property is that each leading entry must be the only non-zero element in its column. This one's a little bit more tricky to think about. But once you play with a couple examples, it's pretty easy to see. So to start off with, if we have this matrix right here, it clearly fails because the leading entries on the diagonal, 1, 1, and 1, they all have other non-zero elements in its row, which are these guys. So it clearly fails. So we can cross that out. But again, if we have 1, 1, 1, 0, 0, 0, 0, 0, 0, the ones are the only non-zero element in each of its respective columns, so this is good, right? And so that's the end. If a matrix satisfies the first three properties from row echelon plus these other two that I just discussed, is reduced row echelon form. And it's also important to note while half the time that every matrix has a unique reduced row echelon form as opposed to row echelon where it doesn't necessarily have to have the same row echelon form. So there you have it, and this is how you find if a matrix is in reduced row echelon form or not. So I think it would be best to go over some quick examples to better illustrate the difference between row echelon and reduced row echelon form. So I have these 5 examples. Each of them is in row echelon form or reduced row echelon form. And I'm going to go through them all to discuss why they're in their respective forms. So first off, we have this matrix, and it is clear just by looking at it that, this is in row echelon form. So we can clearly see this because going back to our properties, there's no rows of zeros, so you don't have to worry about that. And so each leading entry, these pivot points right here, they're to a column to the right of the leading entry of the row above it. So, and it's a little bit wordy. A better way to describe that, it's in that diagonal-like pattern. So it's clearly in such a pattern, and all these entries below these ones right here, these leading entries are zeros. So this is clearly row echelon form. But it's also in reduced row echelon form since every single of the leading entries is 1. And every single leading entry is in a row all by itself. So reduced row echelon form is satisfied very clearly. Second one, using the same logic, there's no rows or zeros. You don't have to worry about it. It's in a diagonal-like pattern. The 3, 1, and -2 are in that pattern, right here, these leading entries. And all these leading entries, they have zeros beneath them right here. So it's easy to see that this is row echelon form, and it very clearly is not in reduced row echelon form since the leading entry of the first column is 3, and it needs to all be 1, so not reduced row echelon. Third column is no longer square, so it's a little bit tricky to think about, but it's clear to see that this is in row echelon form since it's in the diagonal-like pattern, and each of the leading entries is in the diagonal-like pattern, right? And all these leading entries have zeros beneath them. There's no rows of zeros, so it's in row echelon form, and it is also in reduced row echelon form. So we only really care about the leading entries, and each of these leading entries are all by themselves. So it is reduced row echelon form since all the leading entries are also 1. And third one, if we look at the leading entries, these ones right here, it's clearly in a diagonal-like pattern, right? Or like in a staircase pattern, if you want to think about it that way. And so that property is satisfied. There's no rows of zeros, don't have to worry about that. And all these leading entries have zeros beneath them, so we don't have to worry about that as well. And but the only problem that makes it not reduced row echelon form is this one right here. So in order for a matrix to be in reduced row echelon form, it needs to be, the leading entry needs to be in a column all by itself. And since we have this one here, it fails that. So this is not in reduced row echelon. And lastly, we have this matrix, and all the rows of zeros are at the bottom. So it satisfies that property. It is in a diagonal-like pattern, right? So it satisfies that property. And all these leading entries, these 2 ones right here, have zeros all beneath them. So from that, we can tell it's in row echelon form. And it is also in reduced row echelon form since these leading entries have zeros beneath them. This one is not a leading entry, so we don't really care about this. And each one of these leading entries are by themselves. They're also 1. So this is in reduced row echelon form. So there you go, and just some quick examples to help you out.